Imagine reaching blindly into a dark drawer. You know it contains an unknown quantity of red, blue, and yellow socks, but you can't see. Your goal is simple. You want a matching pair. The question is, exactly how many socks do you need to pull out of that dark drawer to absolutely guarantee you get two of the same color? We naturally treat a scenario like this as a game of probability. We assume that because we might get unlucky, we need to draw a high number of socks to safely beat the odds. We confuse likelihood with absolute certainty. But the definitive, mathematically guaranteed answer is surprisingly low. It's 4. This animated diagram shows exactly why. If you draw 3 socks, the absolute worst-case scenario is pulling out exactly one of each color, 1 red, 1 blue, and 1 yellow. Because there are only 3 colors available, the 4th pull has nowhere new to go. It has no choice but to match a color already on the table. This forces a pair every single time. Mathematicians call this rule the Pigeon-Hole Principle. The Pigeon-Hole Principle does not calculate odds or rely on luck. It describes a structural limit. When items outnumber categories, repetition is logically forced. This animated diagram gives us a clear physical model to watch this law operate. We have 4 identical square outlines representing houses, and 5 circular nodes hovering above them, representing birds. Let's play a game. Try to organize these birds so that every single one gets its own private house without any roommates. To prevent repetition, we can deploy the ultimate worst-case strategy. We perfectly distribute 1 bird into each of the 4 available houses. The strategy works exactly until we account for the leftover 5th bird still holding out. We have an n+1 variable. We have 1 more object than we have places to put it. This single extra object acts as a forced trigger, inevitably breaking the isolated distribution and creating a pair. To solve a problem using this logic, you only need to translate the situation into 3 steps. Define your objects, define your categories, and identify the repetition that is guaranteed to happen when the objects outnumber those categories. Mathematicians do not use this principle to predict the future. They use it to map out the absolute limits of a system, and then they let the constraints do the work. Those constraints hold up even as the datasets scale into much more complex territory. Imagine a classroom where you have 31 students who must be divided among 7 different project topics. Look at this grid. We can apply our worst-case strategy again by attempting to divide our 31 students as evenly as possible across the 7 topics, which gives us 28 avatars spread perfectly flat, 4 to a column. But 31 is not perfectly divisible by 7. We have a mathematical remainder of 3 leftover students who still need a project topic. To handle this, we use the generalized version of the principle, known as ceiling notation. The brackets around our division tell us to round any remainders up to the nearest whole number. Those 3 leftover students must join the existing groups. Because of this, it is mathematically guaranteed that at least 1 project topic will be forced to accommodate 5 students. Scaling this logic up even further answers a famous mathematical puzzle regarding the likelihood of finding shared birthdays in a massive crowd. The parameters of the birthday challenge are straightforward. If you put 367 people in a room, you know immediately that 2 of them share the exact same birthday. The calendar acts as the constraint. Including leap day, there are only 366 possible categories for those 367 people to occupy. Mapping the chaotic, infinite variables of human life against a strictly finite set of categories proves that seemingly magical coincidences are actually structural inevitabilities. This logic also applies to the abstract world of integers, where categories are defined by numerical rules rather than physical containers. Consider an entirely abstract challenge. Imagine choosing any 6 random whole numbers from all the numbers in existence. Look at these 5 buckets. Dividing any whole number by 5 yields exactly 5 possible remainders: 0, 1, 2, 3, or 4. With 6 random numbers as objects and only 5 remainder categories, 2 numbers must absolutely share a remainder. This forces a hidden numerical law into existence. Because those 2 numbers share a remainder, subtracting one from the other will always leave you with a perfect multiple of 5. But there's a mysterious limitation. The math proves this shared remainder exists, but offers absolutely no clue which specific numbers it belongs to. The pigeonhole principle does not identify where a repetition happens or which specific objects are involved. It simply guarantees that a shared category exists, turning an observation of chance into a mathematical certainty.